Voyager 2, humanity's most ambitious and longest-serving spacecraft, has again amazed the scientific community with an otherworldly encounter in the dark, distant expanse of deep space. Launched in 1977, far beyond the planets it was initially tasked to explore, this robotic trailblazer has entered a region so distant and alien that even sunlight hardly reaches there. Decades since its odyssey started, Voyager 2 ventured into interstellar space, a realm once thought to be an empty void but now discovered to be filled with unexpected structure and mystery. And in this distant frontier, it found something scientists still have not been able to explain, a pressure barrier, enormous and invisible, that seems to disobey the principles of known physics. This perplexing encounter happened a long way beyond the heliopause, the point where the sun's hold ends and the interstellar medium takes its place. When Voyager 2 passed through this point in November 2018, it became the second man-made object to do so, after its twin, Voyager 1. Whereas Voyager 1's entry had been clean and relatively unremarkable, Voyager 2's trajectory showed something much more complex. Its equipment, more than 40 years old, still operates and gathers valuable information. And what they captured in this boundary area has rewritten all we believed we knew concerning the border of our solar system. It started with a series of unusual measurements from Voyager 2's plasma science instrument. The instrument detects the density, velocity, and temperature of charged particles in space. This should be an area empty of matter, a tenuous fog of interstellar plasma drifting quietly through the emptiness. But what the probe found was a sharp and sudden pressure surge, much higher than any model today could account for. It is now referred to by some scientists as the pressure wall. It resisted the outward flow of the solar wind. It was as if Voyager 2 had encountered an unseen current in a cosmic sea, organized and teeming with energy. This was not a transient or fleeting occurrence. The pressure boundary remained as the spacecraft proceeded, indicating it was a quasi-stable structure, not a fluctuation. It eluded simple definition. It was neither a solid wall nor a distinct magnetic field. Rather, it seemed to be a hybrid zone, a turbulent boundary layer of plasma, magnetic turmoil, and energetic particles that seemed to function like a membrane between the solar and galactic realms. To Voyager 2, floating in space almost 20 billion kilometers from home, the anomaly developed over time. It didn't happen in one instant of change but emerged incrementally. The spacecraft's instruments detected subtle shifts in magnetic alignment, particle speeds, and cosmic ray flux. These readings showed a picture of an ordered, active interface, a kind of cosmic skin that remakes itself according to solar and interstellar forces. What's even more surprising is that this structure was not predicted. Previous models had anticipated a gradual and comparatively quiet entry into interstellar space. The interstellar medium was thought to be smooth, its motions dominated by scale galactic magnetic fields. That concept of running into a structured, energetic pressure wall puts much of that into question. Now, researchers are starting to suspect that this boundary is not a border, more precisely, it's an active zone, defined by the solar system's movement through the galaxy, and perhaps even by adjacent interstellar clouds, shockwaves, or other galactic phenomena. One of the most mysterious effects of this region was on cosmic rays, energetic particles that crisscrossed the galaxy. Voyager 2's cosmic ray detector recorded an unexpected drop in their intensity shortly after crossing the heliopause. That was contrary to expectations. Scientists had anticipated that outside the heliosphere's protective bubble, galactic cosmic rays would become more intense. The drop indicates that this pressure wall doesn't merely exist, it acts as a filter, absorbing or deflecting cosmic rays just like Earth's magnetic field protects us from solar radiation. If that is the case, then it means our solar system possesses a further layer of protection against the perils of outer space, something that had remained completely undetected until now. What makes it all more complicated is the comparison with Voyager 1's experience. That mission entered the heliopause in 2012 without registering the same spike in pressure. Its passage was quite smooth by comparison, with sharper changes in particle populations and magnetic field direction. Voyager 2 encountered a considerably more chaotic and dynamic area, though. That variation indicates that the heliopause is not spherical or uniform. Rather, it could be lumpy, irregular, and variable, similar to Earth's magnetosphere, which distorts and vacillates in reaction to solar storms and magnetic reconnection events. The edge around the Sun, which was considered to be a bubble, looks now more like a beating, reactive shell. This reshapes our concept of interstellar space. For decades, scientists assumed that once outside the Sun's sphere of influence, spacecraft would wander into a silent, uninteresting sea of gas and dust. Voyager 2 has proven that vision seriously flawed. The interstellar medium is not static. Instead, it is filled with turbulence, complexity, and unidentified mechanisms. The pressure wall Voyager 2 ran into has no laboratory analog that anyone knows about. It can be a type of standing shock, a magnetic turbulence region, or something new altogether. Whatever it is, it requires a paradigm shift in our way of thinking about forces sculpting the space between stars. The consequences are deep-reaching, not only for space science, but also for astrobiology, planetary defense, and the course of space travel. If each star creates an equivalent boundary, and if these boundaries differ in thickness, strength, or porosity, then each solar system might be individually protected from galactic radiation. The type of protection could influence directly the evolution of planets, the stability of atmospheres, and even the appearance of life. In that context, the heliopause might be as critical to habitability as a planet's distance from its star. Practically speaking, the discovery influences the design of future missions. Any probe planning to depart the solar system must now take into consideration this dynamic barrier. Its presence suggests possible dangers, fluctuations in radiation levels, pressure variations, particle impact, all of which can threaten instruments or onboard systems. Even communication would be affected, as the structure could affect radio wave propagation or noise levels. Though Voyager 2 has weathered its encounter, subsequent probes will have to be designed with this new environment in place. This also poses a plethora of theoretical issues. Is the pressure wall a long-term feature? Is it seasonal or formed by long galactic cycles? Could it be the effect of interactions between the solar wind and nearby interstellar clouds, some of which the Sun is known to be moving towards? Might there even be more than one such layer beyond the heliopause with its own behavior and dynamics? Until we have a fleet of probes traveling in several directions, we'll never know the three-dimensional shape of this boundary. This absence of spatial information is a significant hindrance. Voyager 2 provides a single line of knowledge through an immense and possibly asymmetric area. Without at least two additional probes intersecting the heliopause at different angles, researchers can't map the shape, size, or motion of the pressure wall. Consequently, a single line of data has to serve as proxy for an entire frontier, such as attempting to characterize an ocean from a single reading of depth. In spite of that, Voyager 2's contribution is revolutionary. The spacecraft has transformed the edge of the solar system from a theoretical boundary to a laboratory of cosmic forces. The information it transmits back to Earth is being applied to update space weather models, to create new simulations of heliospheric dynamics, and to gain a better understanding of energy flow through our galactic neighborhood. Its captures of bursts of particles, patterns of plasma waves, and unexplained drops in cosmic ray density are still confounding and intriguing physicists. And perhaps most amazing is that it occurred so late in the Voyager flight. It's been over 45 years since it left the launch pad, and the probe, which is powered by a tiny nuclear battery, is still operating and still uncovering secrets. Most human-made machines would have given out long ago. But Voyager 2, moving quietly through the blackness, has become a symbol of technological resilience as well as scientific curiosity. This meeting also alters our understanding of interstellar space. No longer can it be thought of as merely a static, unchanging expanse. Rather, it is a borderland, a living, changing interface where our star's influences surrender to the influences of the galaxy. The boundary that Voyager 2 entered might not even be a boundary, but a multiplex transition zone of complexity. As layer after layer is peeled away from the onion, so too does every step from the Sun unveil a new and surprising aspect of the cosmic setting. Forward-looking, the pressure wall will be the subject of inquiry for decades to come. Its composition, dynamics, and meanings cut across the sciences, astrophysics, cosmology, planetary science. It also demands a new sense of urgency in deep space exploration. New expeditions, precisely crafted to chart the heliopause and beyond, could someday reveal what Voyager 2 could only see partially. In the meantime, this solitary probe is our sole witness to an encounter that defies our knowledge of the galaxy's overall structure. If all star systems have a boundary such as ours, then each may be enveloped by some sort of invisible cocoon, a sheath that isolates it from the general currents of interstellar space. Such magnetic membranes, if they are ubiquitous, might be the sentinels of solar systems, determining how they respond to cosmic rays, extraterrestrial particles, and the galactic wind. The implications for knowing planetary evolution, astrobiology, and even the origin of life are astounding. Voyager 2's impossible meeting is not merely a scientific achievement, it is a humbling introduction to the unbounded uncertainty of the universe. In its quiet passage, the spacecraft has shown us that even interstellar space is full of surprises. The pressure wall it met is both a veil and a beacon, a phenomenon that both conceals and reveals, obscures and illuminates. And in reaching out and touching that boundary, Voyager 2 has accomplished something no other spacecraft has. It has touched the very flesh of the galaxy and discovered it throbs with surprising life.